Hello everybody. Yesterday we were talking about the operating systems involved with paging because as we know, paging without the help from the hardware is not that feasible. So we like to know what part of this paging is done by the hardware and what part of paging is done by the software with the operating system. Definitely when we produce the physical address from a logical address or the virtual address, it is a task of the hardware, it is a task of the MMU. Without getting help from the MMU, this translation would be too slow. So MMU helps us a lot, but the hardware by itself is not sufficient to set up all the paging environments and all the paging procedure, etc. So let's look at how the operating system is involved with paging. The first time is when the process is created. As you know, for each process we have a page table. Page table is not a system-wide data structure. We have a page table for each process, and since each process has its own address space, its own virtual address space, the translation of that virtual address space has to be done individually for each process. So each process has a different page table, and that page table has to be set up by the operating system, of course. Okay, so setting up the page table and allocating the space for the process when it started, depending on the working set size, depending on the hint from the application or from the previous runs of the application on that operating system. During the process creation time, page table has to be set up and the space has to be allocated, and necessary linking between the physical memory setup, physical memory pages and the page table has to be done by the operating system. I think somebody has their microphone on and I'm getting some noise. I couldn't find who it is. Am I causing that noise myself, maybe? Okay, it is gone now. That's fine. Okay, good.
We don't hear any voice.
Okay, if you don't hear any noise, that's fine. So this is the first thing that the operating system does regarding the paging page tables. During the process execution time, okay, when we do the context switch, from operating system to the process or from process to process, whatever, MMU has to be reset, because inside the MMU, what do we have? We have the TLB, right? Translation look aside buffer. That TLB has to be flushed because we don't want to keep TLB in a valid situation, because it includes information about the previous process, and we don't want to share that information with any other process, and required MMU stuff. Okay, so who is going to do this bookkeeping about the MMU reset, TLB flushed, and etc.? It's going to be the operating system. Okay, so this is the second time operating system has to do something about the paging, and this part will take lots of this one will take lots of time. Okay, I mean, resetting the MMU or flushing the TLB doesn't take much time, but after that your program will start, your new process will start running a little bit slow. Why? Because all the TLB entries are invalid. They have to be validated. So when they are populated, lots of pages has to be brought back from the disk to the memory, and all the links have to be established, and etc. So that's why we say that context switch is expensive, mainly because of these MMU related stuff. Okay, we previously we used to say that context switch is expensive because we need to copy the registers and load the registers again, etc. Yeah, that's true. It is expensive. I mean, copying the registers and etc. But the expensive part comes from the really this MMU related stuff, cache related stuff. Okay, so this is the second time we are involved with the paging, and the third time is the, of course, page fault. When a page fault occurs, okay, a process calls the page fault, and page fault is detected by the hardware. The hardware says that, MMU says that I cannot find this page anywhere in the page table, so this is a page fault. Okay, so operating system handles this page fault. So detection is the task of the hardware, but loading of the pages and making a decision which page to replace, and that kind of decisions has to be done by the operating system, finding the available pages and replacement, etc. And finally, when we terminate the process, okay, releasing the pages and table entries has to be done by the operating system. Okay, so you might say that just release them. Sometimes, of course, if the pages are dirty, they need to be written back to the desk. So that might be, there might be some work to do regarding the page tables. So 4 times when the operating system needs to get involved with paging. Let's look at this third one, the page fault. Okay, because it is important, it happens a lot. We don't like the page faults, but we cannot avoid it, because at least at the beginning of the program execution, you need to have lots of page faults so that the pages of that program process is read from the disk and is placed in the memory. Okay, so we cannot avoid it, but we should do our best to avoid as many page faults as possible, and we should know what's going on when a page fault happens. When the page fault happens, I'm trying to execute an instruction. An instruction is referring to some memory location, and that memory location, although it is in the virtual address space, no problem, but when I translated that address into physical address in MMU, I see that that page is not in the TLD. It is not in the page table. So that's the hardware trap. Okay, the hardware trap hardware trap informs the kernel that there is something happened bad with the instruction execution. What is it? It is page fault. So before handing the control over to the operating system, like the interrupts, very similar to interrupts, okay, it says counter on stack, and so that we know where we left, and it might save a few other things, but not many things. And the control is transferred to the operating system assembly code. Now the operating system takes the control, and it is given by the hardware, of course. This page fault handling has to be done by the operating system, because operating system registers itself as a page fault handler to the hardware when the system is booted up. Okay, so assembly code routine started to save general register and other volatile information, all the required register and everything, and then the system discovers that the page fault has occurred. Okay, and tries to discover which virtual page needed. Okay, which page is needed to handle this page fault. Once I know the address causing the page fault, okay, I need to make sure that this address is valid, this virtual address, because sometimes that address might not be valid. Even if it is valid, maybe the programmer is trying to write to a read-only page, or read from an execution-only page, and etc. Okay, or there are some protection issues. I cannot make any reading from that page, and etc. Okay, so I make sure that this is not the case. If it is the case, then that's another problem. That's a fatal problem. The program has to be most of the time terminated if that's the problem. If that's not the problem, then I can go ahead. Okay. Number 5, I am going to load some page from the desk. If I need to replace a page, I selected my page. If the page is selected is dirty, it is modified, then it has to be written back to the desk. Okay, so this is going to take some time because writing stuff to the disk is going to take time. So in this case, the book says that context switch takes place because this process has to wait now. But as you have seen, for some of the page replacement algorithms, we don't have to wait for this. Okay, we try to select some other page to replace, some other page that doesn't have the dirty bit on. Okay, but let's say we selected it and the frame selected is dirty. There are no other frames that are with W of 0. So we are going to go ahead. Okay, we are going to suspend our process because we cannot continue. The page that we need to replace has to be written to the desk. Okay, as soon as the time difference between 5 and 6 might be loss of time because to clear the page it has to be written to the disk. It will take lots of time. So when the time comes, when the frame is clean, okay, so operating system looks up discard desk where the needed page is, okay, and another scheduling of the disk operation. So this one, number 5 and number 6, is going to take lots of real time. Maybe not CPU's time, but it will take lots of time for the program. Program has to wait. Okay, so I scheduled it to read it, and I am waiting for an interrupt. When the interrupt happens, okay, that means that I got my page from the desk. When the disk interrupt indicates the page has arrived, okay, table is updated to reflect position, and frame marked as being in normal state. Okay, so we say that I loaded it, okay, and I am marking this frame as it is available, and it is the normal state. Okay, and then after that we are done. We loaded our page, but we need to go back to the program that caused this page fault. Okay, so the faulting instruction that needs that data from the memory has to be backed up. What do we mean by backup? I mean, this will come in a few minutes. There are instructions that accesses the memory more than once. Okay, for example, transfer some part of the memory to other part of the memory. So 2 references to the memory, right? So which memory reference caused the page fault? I don't know. Okay, so that has to be figured out, and the original instruction has to be restored in that way. Okay, and then when I am done, I say that okay, faulting process is now ready to run. I put it in the ready queue, and operating system returns to that routine, or operating system makes a scheduling decision. Okay, when the routine gets the CPU back, of course it is a standard context switch now. Context switch happens, it loads all the register and everything. Okay, so it's a lengthy process, and it is real disk input output, and for any disk input output is going to take some time. Okay, so if you have lots of page faults, if you are trashing, then you are at most spending 1% of your CPU time for useful program work. The rest of them goes to doing input output, lots of input output. Okay, unhelpful input output. Good. Okay, any question about page fault handling? Sometimes you get surprised that such complicated things are happening. Okay, our program while it is being executed is being interrupted, and this kind of very long, lengthy, complicated stuff is happening, and we don't know anything about it. Okay, we don't know anything about it. We don't care. Okay, that's the idea of operating system. Actually, I mean, that's the idea of abstraction of the process. That's the idea of abstraction of the address spaces. As programmers, we don't care about those kind of details. However, they complicated. Okay. However, they are complicated. Uh, we don't care. We write our programs and we execute them. We like to think that things are happening in sequence. This instruction executed, then next, then next, then next, then I do the jumping. Okay. I cannot think about this kind of stuff while I am writing my program, because that would make writing programs too complicated. It is already complicated. Okay, it is already complicated. But if I want to make these kind of things into my programmer's life about the processes and about the memory management, that would make everything so difficult to manage. Okay, so that's the idea of operating system. Operating system is there to hide away the details of the hardware, CPU, memory, I/O devices. Also, operating systems are there to manage these resources, available resources of the hardware. Good. Let's look at this backup stuff. Instruction backup. Okay. This instruction, it is trying to move, as I said before. The instruction is located at this position, the address number 1000, and it has 3 bytes, or 6 bytes rather, yeah, 6 bytes. So it has 2 operands, the operand number 1 and operand number 2, and it occupies 3 bytes in the memory. So when I read this first byte, it might be okay, but when I read the second byte, it might cause a page fault, or the third one, it might cause a page fault. So there are 3 chances, there are 3 possibilities, different possibilities that this instruction can cause a page fault. Okay, and I don't know when it can happen. As a regular user, I don't have that control. Okay, and most of the time I even don't know if a page fault has happened. Okay, so the idea is this: when the page fault happens, backing up, the task of the backing up is this: should I back up my PC count, the program counter, to 1000 or 1002 or 1004? Okay, so I need to keep this information. You might say that I have the same problem with the interrupts, right? While I am executing the interrupts, while I am executing this instruction, if an interrupt happens, it is always possible to wait until this instruction is executed, then handle the interrupt later, right? So when I read this address 1000, address number 1000, and interrupt happened, okay, I may choose to continue read this one and that one, okay, and execute the instruction, whole instruction, then handle the interrupt later. With the page fault, it doesn't happen that way, because I cannot continue. I cannot read the second byte of this instruction. Page fault happened, and it has to be handled. Okay. So that's a complication. After I handle the page fault, I have to do this instruction backup. Depending on which these 3 memory references cause the page fault, the program counter has to be set to the correct address. Okay, so that's called instruction backup, and we are going to look at this during the we are going to look at this when we look at the I/O chapter. I think not next chapter, but the other chapter. Okay, good. Okay, paging is very useful. It helps us a lot in abstracting away the details of memory sharing, etc. And page faults happens and we have to handle it. But sometimes some complicated situations may arise, such as this. I I start an IO read as a process, and I block obviously because IO is going to take some time. Okay, whatever the data that will come from the disk will be. I asked the operating system read some data from the disk and put it in this buffer. Okay, as soon as I executed this, I am blocked. I am waiting for this to complete this task. But the buffer that I am holding is in the memory, of course. It has pages. If somebody else, if somebody else replaces my page that is waiting for the buffer, so when the data is ready, it has nowhere to write it. Okay, so data is ready, but the memory that is supposed to have that data is not in the memory anymore because it is paged out. Okay, so what are we gonna do to prevent this? Some pages might be locked or penned. So you are saying that this page is going to stay in the memory. Okay, because this is important. You cannot replace it. Okay, or maybe we could do all the IO in the kernel buffers, and kernel buffers are special buffers, and they are penned. They are not supposed to be replaced. Maybe that might be another solution, but if this is the solution, then I have to do the IO in a kernel buffer. After that, I need to copy that data from the kernel buffer to the user buffer. Okay, so this happens and it has to be handled. Good. Any questions? Our quiz will start at 12:30 and it's a 10-minute quiz. There are 2 questions. Backing store, we kind of started talking about this, but we didn't go into details of it. We never looked at the details of where we keep the data on the desk, where we keep our pages on the desk. Okay, that's called the backing store. Where do we store the pages on desk? Okay, the simplest algorithm is this. Okay, this is our main memory. 4 pages are in the memory. The rest of the virtual memory is not loaded. So where are they? They sit on the desk like that. Okay, so let's say my virtual memory has 8 pages. My main memory can hold only 4 pages. So 4 pages in the memory. Okay, the rest of them should be on the desk. But this approach, the approach number 1, okay, keeping all the virtual memory on the desk is wasteful. Why? Because I am keeping these pages in the memory, and on the desk I have also some position for them too. So people realize that, they say that, okay, let's not do this, let's not do this, let's do it this way. If a page is in the memory, okay, don't keep them on the disk swap area. Okay, so on the swap area you have only the pages that are not in the memory. So the second one is called dynamic backing up. The first one is a static one. Okay.
Sir, I didn't get this. In the first figure, can you go there?
Yeah.
I don't see the pages that are in the memory being in the disk.
Well, see, this is our page table, right?
Correct.
Page table has links to the memory, like 4 and 3 is here and 0 is here, right? So there are 4 pages in the memory. Okay, but also there are pointers to the desk. So for each page, there is a position page available on my desk. See, this is the size for the whole virtual address space.
So even if we don't hold them in the disk, they have a position. Thus, they keep a.
No, well, the numbers may not be there, but I mean they are there, right? This is 3, 4, and 6.
Oh, okay. I
Okay.
thought because it was a pointer, it wasn't there. So.
No, the pointers are already there, and I mean, whenever this, if you are paging this out, and if this is dirty, you need to write it to this position. Okay, nowhere else. Okay. So I know the position for page number 6, it is always fixed on the disk. Whereas for the dynamic approach says that I don't, okay, my page table has a, of course has this map first. This one, this one, this one, and this one. This for the memory. But it has a disk map. This map keeps only the pointers for the pages that are in the disk only. So when this number 6 is paged out, dynamically I create a place for it, and I take a pointer to that one. So the swap area is dynamically growing and shrinking.
I have another question. Let's say our main memory is way too big, like 2 terabytes of main memory. Does it still
You mean your
disk?
virtual memory is too big? Is that what you're saying?
Correct.
Yeah. So your virtual memory is big. It is. We measure it nowadays. We measure it on the orders of petabytes, right? So your virtual memory is petabytes. What is the virtual memory size for 64-bit Intel CPUs? I think it is 2 to the power 48 or something like that. It is so big. So you are saying that I cannot, even the disk space will not be enough for this kind of a memory space, right? Considering that you need to keep this page table for each process separately. That's what you are saying, right?
Well, I don't think that was what I was saying because
Okay.
I was asking if we have a big enough memory that we don't need disks. Does it still write to the disk even if we don't need that much space in the memory?
Well, you will never have big enough memory. Okay, as I said before, I mean, the for the 64-bit processes, this is the virtual memory size. Okay, this is the virtual memory size, and nobody has that kind of a memory, and this is just for a single process.
Okay, I see.
And in
It's
fact,
always big disk.
most of the time you won't have that kind of a hard disk space either. So how does it work? I mean, how does it work? It works because most of the processes, they use only very small fraction of this space. So if some pages are not used at all, of course I don't keep them on my desk. Okay.
I see.
So usually we have this dynamic swap area, and you know this, right? When how many of you installed Linux operating system? Raise your hands. How many of you installed Linux operating system? Well, I am expecting to have more than 100 hands right now. Okay, good. No, not good. How come you guys? Okay, at least out of the people who are listening to me, okay, many of you have installed the operating system. When you install the Unix operating system, Linux operating system, it asks you to determine the swap area first, right? Okay, how much disk space would you like to keep for the swap area on the desk, and you make a decision. Usually it makes a suggestion and etc. This is the swap area that swaps the pages, okay? So that swap area is going to be used a lot. And usually we like to keep our swap area on our SSD devices, right? Because SSD is so fast compared to the mechanical hard drives, and when paging happens, when you swap your pages, when the page fault happens, etc., it's going to be maybe 10 times or 50 times 50 times faster than the hard disk version. Okay, so this is called the swap area, and usually for our modern day operating systems, the swap areas are dynamic, and this is called the backing store. Backing store. Good. Any questions about this
Sorry,
backing?
can I ask a question?
Sure.
So you said that the virtual memory is too big for a 64-bit operating system.
Yeah.
So do we just like assume that the program is not going to use most of it, just a tiny fraction of it, and just ignore the rest? What if the program actually uses something like above our assumption?
Yeah, exactly. I mean, we don't assume it. We know what part of the virtual memory the program is using, right? It is accessing it, either writing it or reading it. As soon as it writes it or reads it, okay, we know that it is using that part of the virtual memory. So that part of the virtual memory has to be paged. There has to be a physical page frame in the memory, and we have to have a corresponding swap area on the desk. But usually we don't have those kind of large programs. I mean, if you try to do it that way, okay, you will be out of the swap area soon, and your program will be terminated saying that this program is using too much memory. I mean, you cannot have a single process using this kind of memory, right? Because we don't have enough swap space for that one. Definitely, we don't have enough any physical memory for that one. So these are the limits put on by the hardware and the fundamental design of the operating system. So why they are putting these kind of very large limits? Well, as I said before, what did they say? What did Microsoft say? I mean, I don't know if this is true or not. They say that 256 kilobytes of memory should be enough for everybody in 1980s, and they designed their operating systems that way actually. Okay, they designed their operating systems that way. Then later, then they see that it is not enough, so they made a decision that 640 kilobytes should be enough, and they changed the operating systems, and they realized that it doesn't happen. So this earlier versions of those operating system, 640 kilobytes was the upper limit for the whole operating system, not for a process, but for operating system. Okay, even if you have more than 640 kilobytes of physical memory available on your system, the DOS operating system couldn't handle it. You had to do lots of. They had to do this. Um, remember the what do we call them? The you load the pages in and out layers. Okay, by programmers they say that okay, I am going to load this part of the program first. Then when I don't need it, I am going to load the second part, etc. They had to do that kind of stuff. So in order to stop these kind of problems, when they design the later versions of the processors, they say that okay, this will be the virtual limit, and nowadays, I mean, this kind of a limit was enough for us. Okay, for the last 20 years, maybe, yeah. Okay, so uh, important concept. We talked about this a little bit, but it didn't make much sense then. Let's look at this concept with the help of the memory management. Separation of policy and mechanism. Okay, it's a very important concept for the general operating system design. We like to keep what is policy. Okay, for example, our scheduling policy might be priority scheduling. For what is the priority scheduling? We let the higher priority processes use the CPU before the others, before the lower priority. That's our policy. Okay. Another policy could be, okay, I am going to do the least recently used page replacement. That's our policy. Okay. To implement these policies, of course, we need lots of code. Okay. And that code might be complicated code, but they have to be implemented. On the other hand, there is a mechanism for doing things. It's like this is the brain of the whole thing, and these are the hands and legs of the algorithm, you could say. Mechanism, if you are going to do any CPU scheduling, okay, if you are going to do any CPU scheduling, you need to have access to protection bits of the CPU, right? Okay, when you need to switch from one process to another process, okay, when the timer interrupt happens, somebody has to handle it. Okay, operating system handles it. So these are the mechanisms of doing stuff. Playing with the protection bits, okay, setting up the MMU, reaching the TLB buffer elements of it. These are all the mechanisms. Okay, so if we keep the policy from the mechanisms, if we keep policy and mechanism on different sides of the picture, we can write our complicated policy code, and I keep it separated from the mechanism. Mechanism is very delicate, because if you make a simple mistake, you are playing with the whole computer, and you are very powerful. You are changing your MMU bits, CPU bits, and etc. So it has to be coded very, very carefully. So keep the mechanism code at a very small part, okay? So write a very careful mechanism part. Also, the mechanism usually is machine dependent. It depends on your CPU, it depends on your memory structure, and etc. Policy is not that way, okay? Policy is, if I ask you to write a page replacement algorithm in C, okay, you could write it, and it would be a general policy page replacement algorithm, and you can port it to different operating systems. Okay, that's what we are going to do with the that's what we are going to do with the memory handling, or the page fault handling, or the virtual memory handling. Okay, so we have three parts of the system. A very low level MMU handler, that's part of the mechanism. It is written as assembly. It is machine dependent. It has to access lots of important parts, privileged parts of the hardware. Okay, and then we have a page fault handler that is part of the kernel actually. It is machine independent, and it is for mechanism for paging. Okay, so these two are low level stuff. Okay, they run in the kernel, and they are the mechanisms for paging. And then I have the third part, maybe the most important part, that will make the difference. Okay, an external pager running in the user space. It is the policy. So this one makes a decision which pages are going to be replaced. Okay, how am I gonna do all the demand paging decisions? How many pages I am going to keep? How many pages I am going to keep available all the time, and etc. So this is the brains of the whole memory management. But I like to run this in the user space. I don't want to make my kernel more complicated. Okay, and this is machine independent again. I can take this external pager and put it on another operating system, and it will work. So this picture is nice. When the user process causes a page fault, it causes a page fault. It doesn't know that it caused a page fault. It tries to the kernel. Okay. Page fault handler, okay, determines which page is needed, and it hands this information to external pager. External pager is a operating system process, but that process runs in the user space. That external pager handles all the details, which page to replace, okay, which one is going to be loaded, and how I am going to update all the page tables and etc. It makes all those decisions. It requests the page from the disk. It gets the page and it hands the page to the fault handler in the kernel space, and the fault handler puts the page in the MMU, and our process is ready to run again. So the code in the running in the kernel space is mechanism. It is simple. I wouldn't call it simple. It is small lines of code. Okay, this part is definitely machine dependent. This part is not machine dependent, but it has to run in the kernel space because it is accessing the MMU bits and the parts of the memory and etc. But this one runs in the user space. It doesn't have any access to those privileged stuff. Okay, so it is responsible for getting data to the disk and out of the disk. Again, this is an operating system process. You might say that as a user process, this one has lots of privileged data, right? Because it is responsible for putting data to the disk and getting it from the disk, and this one can see all the data of all the processes, right? Because this one is the one that writes data to the disk and reads the data from the disk, and all the data belong to the other processes, you might say. But as I said before, this one is a operating system process, and all the processes are protected from each other, right? They cannot see anybody else's data. So it is protected by the operating system. Good, okay, so we have these kind of techniques for other tasks of the operating system, such as the scheduling, CPU scheduling, or the device drivers, or the file input output, etc. So we like to keep our policy in the user space so that we keep it machine independent, in a machine independent way, and we keep it as portable as possible. Good. Any questions about the separation of the policy and mechanism? Okay, no questions, it looks like. Then I will continue. Okay, so split from the mechanism. The policy code cannot have access to R and M bits, okay, read bits or the modified bits. It is not available for the external pager. So that's why you might need many switches back and forth between the user space and the kernel space. It is slow, yes. System calls are slow. The communication through this line is slow. This number 2 and 5 and etc. This is slow, but it is worth doing it. So this is very modular and easier to manage. Operating systems are very complicated. You have to make some compromises to make things more modular and manageable. Okay. If there are no questions up to now, I will start a new topic called segmentation. And the segmentation is kind of an alternative for paging. Okay, kind of an alternative for paging. And although it is not used much as it is by the modern operating systems, either Windows or Linux, it is worth looking at it. It's a good idea, and it was invented some time ago. and you are going to see that it is useful. Okay, so far we said that our users, our programmers, our programs don't know that they are using a virtual memory. Okay, they say that I have a 4 gigabytes of memory for a 32-bit computer. I have 4 gigabytes of memory and I can do whatever I want with that memory. That's it. Okay. They don't care about the pages. They are not allowed to see the details of the paging. That's it. Segmentation idea says that why don't I give the users segments, program segments? Okay. Because for many programs, there is lots of data and each type of data can get large or can shrink to some small amount, can get large again. So how am I going to handle this complication even in a um, paged version? For example, if you are developing a compiler, okay, the compilers has to keep a symbol table, which is a table of all the symbols, global symbols, local symbols, etc. You have to keep them in a symbol table, and you have to keep the source text, your input program to be compiled in the memory, your constant table, your parse trees, your call stack, etc. So you need to keep lots of data in your memory as a compiler program, and you don't know the sizes of each data type. Your source text could be very, very large or small. Your constant table might get very, very large or small. But it's the same with call stack or the parsed trees. So if if I organize my virtual memory like that, what happens if this empty area in the source tag is not enough for me now? I need to move my constant table up. Maybe I need to move the whole parse tree up and etc. So I need to do lots of moving within my virtual address space. That's going to take lots of time. People who invented segmentation, they said that let's give the programmer segments. The programmer says that the programmer says that the operating system that I need 1, 2, 3, 4, 5 segments, and each one has its own address space. Segment number 0, I am going to use it for symbol table. Segment number 1, I am going to use it for the source tag. Segment number 2, constant, and etc. It goes that way. So the program knows that it has 5 segments, 5 memory segments, and if I need to, I can grow these segments or I can shrink them with the help of the operating system. So I don't have to copy anything from one place to another place. Managing all these segments and how the segments are stored in the memory are handled by the operating system. I don't care. So instead of having a one single large virtual address space, I have many virtual address spaces. And these address spaces can grow and shrink. Okay, so that's the idea of the segmentation. That's the idea of the segmentation. Yes.
Do we keep these segmentations separately in the memory?
You mean we as programmers or we as operating system designers?
As an operating system designer. It's not sequential in the memory, is it?
Well, that's a good question. Then there's an operating system design question. How do I keep those segments, right? Yeah. So that's what we are going to look at in a few minutes. Okay. But for the end user, for the programmer, I don't care. All I care is that I have 5 segments. Okay. And if I need to, I can take 5 more or 10 more, 100 more. Okay. And each one is a different virtual space, and I can use them as I want. And I don't care where they are stored in the memory. Okay. And I don't care my total memory size is larger than the memory, and etc. Okay, it looks like I'm out of time. Let's take 8 minutes of break. At 12:30, your your quiz will start automatically, and you will have 10 minutes. And at 12:40, we are going to we are going to start restart our discussion on the segmentation. Okay, break. Okay, your exam has started.
Hocam
Sir, I
exam
didn't
gelmedi
receive.
ama. Evet, bana da gelmedi.
Wait a few minutes, a few moments. It will be available. Did everybody get the exam?
No.
Not yet, sir.
No, I'm still waiting.
Nobody got the exam?
Yeah. Not yet.
Now I got it.
Okay. So there is a 1 minute difference or something like that.
Sir, when I click the link, it says it's unavailable.
Click again.
Same for me. Yeah, me too.
Click again. It will be available in 1 or 2 minutes. If it doesn't work, just leave Teams and log in again.
Hocam ben hala açamadım.
Ozan, try again. Log out and log in. Anybody else having a problem?
Okay hocam. I mean.
Everybody is in. Okay, good. Your time is almost up. When it is 12:40, you cannot submit anything. Okay, be careful about that. So submit your answers right now. It looks like 119 people submitted it. Anybody who didn't submit the answers? Okay, good. Okay, maybe I should just go over the exam a little bit. Where is my exam? Let me find the exam. Yeah, okay. It was a simple exam. I think many things. Why do I? I'm looking at somebody's. Okay, questions. Yeah. So the first question is this. I took this Intel 386 processor, a page table entry, and I asked, given the fields of 386, explain which elements are required by the second chance page replacement and NRU. Remember, the second chance page replacement keeps all the pages in a queue, but a queue, and it looks at the beginning of the queue during the page replacement. If the R bit is 1, then it puts the page at the end, and if it is not, then it replaces it. So it definitely needs the R bit. Okay, so R bit is here in this case accessed. Okay, D is dirty. Okay, it is right. A is accessed. Cache disabled, we don't use it for the second chance. What is write true? Does anybody know what write true is?
Is this modified bit?
No, modified bit is dirty bit.
Okay.
What is write true?
Q to be written at the disk.
Say it again.
Q to be written at the disk.
Why would you keep that in the page table entry? I mean, all the fields here are to be used by the MMU, right? If I am modifying a page, I make this dirty bit 1. If I access the page, I make this access 1. Okay? If cache is disabled for this page, I don't load this page in my cache. What is right true?
of writing mechanism, write back and write through, but I couldn't remember the details.
Write through means write through is this. Whenever whenever you write to this page, okay, always write it to the memory. Okay, always write it to the disk, sorry. Okay, if you are modifying something in this page, always write it to the disk. So don't keep any modified pages in the memory. Writing has to be done in the disk. Reading is okay, you read it from the memory as much as you like, but if you are writing to that memory location, that writing has to be done to the disk. What is the advantage of it? This page doesn't get dirty at all because you are updating your disk. Okay, what is the disadvantage? The disadvantage is, of course, what?
It's slower.
It's very slow, right? I mean, writing is very slow. Writing is very slow. That's why you don't make your default behavior write through. But for some pages, for maybe some important pages where everything has to be kept updated, maybe they could use this one write through. Okay, and user supervisor. Okay, that page is only usable by a supervisor. And arbit is this a read-only page or write-only page, and etc. P is for present. So for the second chance page replacement, I need the access bit, and that's it. For the NRU is the first one, the most simple one. Dirty and access bits are the ones that are needed. Okay, so this is the first question. Second one, do we need timer interrupts to measure the PFF? What is PFF?
Page fault frequency.
So do we need timer interrupts to measure it?
Yes.
Try again.
I think no.
No, why would you need the timer interrupt for PFF?
Isn't
use
PFF like
clock
a,
interrupt.
When page
when
faults, when
happens
page
in
fault
live?
happens, you know what process caused that page fault, and you can update the page table of that. You can update the process table of that process, right? Causing that this process caused this fault. So you know the PFF for that process, and you can update it during the page faults. So the answer is no, but just saying no is not a good answer. You need to explain it. Okay, good. Let's go back to the segmentation again. Segmentation is something that is, again, supported by the hardware. Without the hardware support, segmentation would have been very, very slow. And the idea of segmentation is this. Your user, your programmer can say that, okay, I need 10 segments or 15 segments, and I'm going to use them for my own purposes. A segment is a logical entry, and the programmer knows about the segments. Okay, this is very different from the paging. Paging is a logical entry too, something virtual, but about the paging, the programmer doesn't know anything about. Okay, but the segmentation, the programmer knows about the segment. Of course, the programmer doesn't know how the segments are handled, how the segments are stored in the memory, how they are swapped to the disk, and etc. But they know about the segments. They say that I am going to read this data from this segment. Okay, a segment might contain a procedure, array, stack, collection of scalar variables, whatever. So it depends on your program design, software design. It's up to you. Okay, imagine that for each library function you have a different segment, and that segment is shared between many programs. So that would be very useful. I wouldn't have any uh, uh, position independent code problem. Okay. So if a procedure occupies a separate segment, that's what I'm saying, with address 0 is starting address, the linking of procedures compiled separately is greatly simplified. So all you need to do is you need to know the segment number of that procedure, and you just make a call to that segment. That's it. Okay. So let me show you this nice table just to show you the differences between paging and segmentation. Okay. The programmer doesn't know about paging at all, but segmentation definitely the programmer has to know about. So with the paging you have only a single single linear space, but for segmentation the idea is you should have many. Okay. And of course for both of them the total area used by the process can exceed the physical memory size. Both of them are virtual addresses. Okay. Can procedures and data be distinguished separately and protected? For the paging, since I have only a single linear space, for paging it is no. For segmentation, yes. I could put my code in a different segment and data in a different segment, of course. Okay. If I have large tables with the paging, you have to adjust the size of your tables yourself with programs, okay? But with the segmentation, you get help from the hardware. Okay. So data sizes that fluctuates, that changes can be handled nicely with the segmentation, but not with paging. Okay. Is sharing of procedure between users facilitated easily? Okay. Share procedures, put the procedure in a different segment and share them. Yes, segmentation can be done. Paging, I wouldn't say directly no, but let me put it in the quotes. No. Okay, because remember, we could have shared pages, and within that shared pages, I can have my own procedures, but since the user doesn't know about the pages, where that procedure starts, which pages are shared, etc., the user doesn't know about them, so that might be a problem. Okay. So what was the motivation for paging and segmentation? The common motivation is abstracting the memory. Okay, invent the address space. But the specific motivation for paging is to get a large linear address space without having to buy more physical memory. Okay, for the segmentation, it allows programs and data to be broken into logically independent addresses. Okay, so that will help us in sharing and protection of the data and the code. So that these are the differences between paging and segmentation. We like to kind of show it as an alternative ways of doing the memory, but usually you use segmentation with paging. So this is what we do. This is what we do. Okay, let's say this is my segment number 0. I divide this segment into physical pages. So I have 1, 2, 3, 4, 5 pages here, 3 pages, 1 page again. Okay, so I can page each segment. Okay, I don't have to keep all the segments in my memory. Maybe I can take this segment and this segment in the memory. The rest of them can sit in the desk. So I have the best of both worlds. Okay, many linear address spaces for a procedure, for a process, and each segment is paged, and the user doesn't know anything about that. Okay, so you can have as many as I think for most systems there are 2 to the power 10, so there are 1024 segments could be used. So more than 1000 segments is available, and each one is paged. Okay, so in this picture, I mean, this is how the segments are stored in the memory. This one needs to be compacted from time to time. But if you use the idea of paging with the segmentation, okay, this is pure segmentation. We don't like pure segmentation much because it has this compaction problem, external fragmentation problem. Okay, so if we use segmentation with paging, we solve all of these problems and we get the best of both worlds. Multics is the system that invented operating system, you know that, right? That invented many techniques that we are using today, or initialized it or made it popular. Okay, as you know, Unix is invented by two people who worked for the Multics projects. Okay, by jokingly, they call it Unix because this is multiplexed. I forgot the name. Some service computation, some service I forgot the name, and they make it okay. They think that the multics was okay. They think that the inventors of Unix, they thought that multics is unnecessarily complex. It is over designed. It is over complicated. Okay, and it is trying to achieve too much. So we don't need that. Okay, let's keep it simple because in 1960s we don't have those kind of hardware, okay, to support all the needs of the multics. So they scaled it down a little bit. They took many ideas, but they didn't take any code from the multics, and they invented Unix. Okay, so it influenced Unix a lot. Also, the multics, it's running on a computer that the Intel platform borrowed lots of ideas from that platform. TLVs are invented by Multics, translation local site buffers. Also, the main idea of Multics is actually cloud computing. So they say that you buy electricity from a company, you buy your gas from a company, you buy a telephone service from a company, and you are going to buy a computing service from us. Okay, so we are going to give you computing service over the communication lines. That's the idea of the cloud computing, right? So the first time it was used is 1969, and they kept using it until 2000. It is the same operating system. It is not a Multics version 1 or 2 or 3. Okay, you might say that the Apple operating system is 30-year-old operating system. No, Apple made a major revision to its operating system like maybe 6 years ago, maybe 10 years ago. Okay, so it's a new system. You might say that Windows is a very old operating system. No, it is not. The original version of Windows is very different from today's Windows. Okay, but Multics was used, okay, from 1970 to 2000 for 31 years without major change, major change. And the reason why they stopped using Multics is they they couldn't find the hardware that it needed because nobody was producing that kind of hardware anymore. Okay, so why are we talking about Multics all of a sudden? We are talking about Multics because we like to see the segmentation with Multics. Multics uses the segmentation. So each address has a segment descriptor, so it is 36 bits. That's a very large number of segments actually. Okay, so each segment descriptor points to a page table, and I have many page tables in my memory. So for a Multics address, there is this segment address first, and the page table address the next, and the offset inside the page table. So this is what it is. Okay, main memory address of the page table. Okay, this is the segment descriptor inside this table, total of 36 bits. Okay, so for each segment in my memory I have one of these. There are total of 2 to the power 36 segments. Okay, when you look at one of them, it says that okay, my segment lives in this page address in the memory. That's what it says. It's the main memory address of the page table. So it points to this page table, and that page table is in the memory. Okay, right. And then I have in 9 bits, I specify the segment length in pages. So each segment could be at most 2 to the power 9, that is 512 pages. So what is the size of the page? Multics supports multi-sized pages. Your pages could be either 1 kilobyte or 64 1 kilowords or 64 words. Okay, so for that day, the 1 kiloword is a large page size. So that means that each segment could be 2 to the power 9 times 2 to the power 10, 2 to the 19. So 512 512 kilobytes each segment, right? 220 is megabyte. So for 1969 it is large. So it's, if the segment is paged or not paged, okay, could be that segment could be a simple byte addressable page or paged stuff, and there are some operating system private bits here and protection bits, read, write, execute. Okay, so this is the structure of multics paging, segmentation with paging. As we said before, segmentation by itself is not a very useful thing because you have this problem of external fragmentation and the compaction problems and etc. Okay, and this is a 34-bit multics virtual address. Each process to address a byte in the memory has to specify this. First, you specify the segment number, then your page number, then inside that page you have 10-bit offset. Remember, we have this 1 kiloword pages. Okay, this is the address in that page. So the page number, segment, page number, and so there are 2 to the power 6 pages in each segment. Okay, and within that page you have this one. So total of 2 to the power 36, very large virtual address space for a computer of that day. And I think the total memory was like maybe 1 megabyte or something. I think it was 2 to the power 20. 1 megabyte is the total memory available, the physical memory available for this multics computer. Okay, good. Okay, I already talked about this. And this is the TLB, the first time it is used by multics. TLB structure of the multics operating system. Okay, each entry a valid bit. See, it has the age field, so they are measuring the ages of the pages, and the protection, read, write, execution. Okay, and the segment number and the page virtual page. Okay, so this is the comparison field. Remember the segment number and the virtual page. When you specify these two numbers, okay, since this is an associative memory, you look it up. This is the comparison field. You look it up, and if it is in there that you find it, then the corresponding one is the page frame. This is the physical page frame that maps to the memory. Okay, so these numbers are unique. These numbers are unique. If it is in the TLB, then I use it. Otherwise, I have to load it from the memory, the large page, segment page table, etc. Good. Intel 86 platform tried to do similar stuff with the segmentation. Okay, since it is not used much with our modern operating system, the idea of segmentation, I am not going to look at it. Okay, but Intel 386 supported the segmentation. Nowadays, either Windows or Linux, I think we are using only 4 segments. We are using segments, but they are only 4 segments. User code segment, user data segment, kernel code segment, and kernel data segment. So these are just 4 segments that we are using. Even though the processors are capable of supporting many more segments, we are using only 4 of them. And I think Intel dropped support for large number of segments when it switched to 64-bit processors. That's what I think. But still we have these 4 segments. Okay. So the kernel ones, usually as regular programmers, we don't care about them. Okay, user code segment and user data segment. Usually compilers produce code for that kind of segment, and we don't mix our code with the data, right? Okay, good. I think that's end of this chapter. I am not going to talk about again Intel structure, but it's very similar. You get this one. This directory is the segment number, and inside the directory there is a page number, and there is offset. So the total of 32-bit address. So virtual address, this is the 386 structure, 32-bit processor. Segment number, page number, and inside each page. So it looks like 4 kilobyte pages here. Okay, the idea is again same with the multics. Good. If there are no questions, I will start the new chapter. Are there any questions? So we looked at the abstraction of a process. Okay, abstraction of the CPU. Then we looked at the abstraction of the memory. Now we are going to look at the abstraction of the secondary storage.
Okay, sir. I have a question about today's quiz. So about the PFF file, page fault file,
Yeah.
page fault frequency.
Uh,
Maybe I understood it incorrectly, but isn't that we try to simulate real life performance with it, or measure real life performance? So can you just remind me why cannot we, or why shouldn't we be using interrupts to simulate real life performance with that?
well, the question doesn't say that should you use it or not use it. Do you need the interrupts? Do you need the timer interrupts to measure the page fault frequency? Okay, the answer is no, you don't need it. You don't have to. I mean, you could use it to come up with a nicer page fault handling algorithm, but in theory, you don't need it. All you need is the page fault interrupts. That's it.
Oh, so the question was targeted towards the measurement, not the actual page fault.
The question was, where is the question? Question, do we need timer interrupts to measure PFF? The answer is no, we don't need it. That doesn't mean that if I am using the timer interrupts to make a more realistic or more efficient, I wouldn't say realistic, but more efficient PFF measurement, yeah, you can come up with anything. I mean, it is okay if you have the timer interrupts. Why not use it to make a more efficient PFF measurement? But in theory, you don't need to use the timer interrupts for PFF.
All right.
Okay, any other questions? So the memory is as important as the CPU, but files are important too. Maybe they are not as important as the memory and the CPU, but they are one of the main concepts of the operating system abstraction. Okay. All the computers, whatever they are, you need a way of storing long-term information. As you know, for a regular computer, when there is no power, you don't keep any information. You are not executing anything. You need power. If the power goes off, okay, I don't have the power, I am not using the computer, then where am I going to keep my data? Okay, so it must be possible to store a very large amount of information that someplace, okay, and that large amount of information should survive termination of process using it, and that data, wherever it is, it should be accessible to many processes, multiple processes, and these all have to be monitored by the operating system. Okay, so we need a new abstraction. The new abstraction name is the file. Okay, now we have invented file. Before we have invented processes and threads, then we have invented address spaces. Now we are inventing files. Three things, okay. Operating system abstracted away the concept of process, chapter number 2. Chapter number 1 was, I think, introduction, yeah. And then chapter number 3, we invented virtual address spaces. Now we are going to look at this file. Together, the abstraction of processes, okay, address spaces and files are the most important concepts relating to operating systems. Okay, if you really understand what these three concepts are, you are well on your way to becoming an operating system expert or conscious user. Okay, so we need to look at the details of the files. We need to look at the files, how we achieve this stuff. Store very large amount of information and keep that information safe. And regulate the access to that file. Previously, I mean, what would you do if your program crashes? As a programmer, what would you do if your program crashes?
We log to a file.
Restart.
Yeah, we restart it, right? Just that's it. I mean, if a program crashes, there is nothing I can do. That's it. We restart it. But if we have a crash while writing to a file, or if we lose one of our files, then we are in trouble. We are in serious trouble, because that data is supposed to survive, okay, termination of a process, okay. That data is supposed to survive for days, for months, for years, okay. So the problems are a little bit different. We need to be careful about our data, okay, how safe our data is. Is it consistent? If something happens to my data, can I recover it? These are the kind of things that the operating systems are responsible for. Okay, so as a user, I give my data operating system, keep it on some secondary storage, and I like to be able to access it whenever I want, and I like it to be safe. Okay, and many processes are going to do that. Remember what I said? I said that on this computer, I have hundreds of processes running at the same time, right? I have hundreds of processes are running at the same time, more than 100 processes. So that's one thing. So each process has a simple process ID, and I can refer to that process using a simple process ID. Compared to number of processes, the number of files is much larger. Okay, I have millions of files on my system, on this computer, and I have another way of finding my files on my desk, and I should find ways of updating those files, reading them, modifying them, and etc. So these are all the problems that has to be solved by the operating system. Okay, the interface to a file is very simple actually. I mean, if you have a file, as a regular user, this is what I do. I read block K and I write block K. So a file, as a regular file, the the virtual concept of a file, let's say file A, has blocks. Okay, and what I can do is I just read block number 10 or write to block number 12. That's it. So this is the concept of a file, a linear sequence of fixed size blocks. So it's like a linear address space, but I have many of them. I have millions of them on my this device, whether it's a mechanical device or solid state device. Okay, so this is as simple as this. Not many things can happen with files. Just I make a new file, delete file, I read from a file, I write to a file, and these are the basic things. That's it. So why is there a complete chapter about these files? But files are important, and you're going to see the problems that we are going to have with. Okay, good. So some questions. How do you find your information? How do you find your file? If I keep all of files just next to each other, or 1 million of them, if I give numbers to each file, like the process numbers, okay, finding files would be easy. You would say, give me the file number 300,571, etc. That would, operating system would give you that. But how, as a user, as a regular programmer, how would I remember those numbers? That wouldn't be a very good. Way of keeping the file. So how do you find your information? How do you provide protection? Because the users are not supposed to see each other's data, whether in the main memory or on the desk. Okay, so I need to provide this protection, and I need to manage the space, the disk space that I have. How do I know which blocks are free? How do I know which blocks are used by whom, etc.? So these are the things that we need to be addressing here. Okay. So for a file system, to function properly, we need some design decisions. What are our file names? I mean, are the files going to be simple numbers or file names? If it is the names, what are the conventions for the file names? Okay, so, and the structure of the files, directory structure, hierarchical or not hierarchical. Okay, types of access control, can I read it, write it, execute it, etc. Versioning of the files, different versions. Fault recovery, what happens if something happens, something bad happens while I am writing to a file? Okay, can I recover from that error? Other file operations, and many more. So these are all design decisions when you are designing your file system, and we are going to look at them in this chapter one by one. But for some reason, what happened? Let me open this, because I have only 1 or 2 minutes, in a very quick browser. Okay, So let's start from the first design decision, files and names. Okay, so each file has a name. This is the convention. I mean, whatever operating system you look at, whatever file system you look at, we give names to files. Okay, file is an abstraction mechanism, and it provides a way to store information on our secondary storage and read it later, and we give names to it. Usually the file names are case sensitive for operating systems like Unix, okay, and usually we have extensions, okay. For Windows, extensions are required, okay. Extensions are required. Each file is supposed to have an extension. Executable files have the extension of .exe, okay. Document files have an extension of doc, right? Those are the stuff. And different operating system takes the extensions differently. For example, for the Unix operating system or the Linux operating systems, file systems, extensions are not required, but they are permitted. And usually they are uninterpreted. Okay? And
But also, Windows does have files without extensions, or you can create files
well,
without extensions.
in that case, the extension is null. Okay?
Oh, okay.
It has an extension, but you don't use that part. But for Linux, extensions are not permitted because, I mean, for Linux, dot is the character dot, I cannot write here. The character dot is just a character of a file. Okay? So that's why you can have abc.ce.c. Okay? Yeah, you might say that how does the compiler know that I have a C program, etc. I mean, the operating system doesn't care if it's a C file or the text file, but the compiler cares, of course. For the compiler, extension is meaningful, but for the operating system, extension is not that meaningful. Okay? And the length of the extension or the file name, MS-DOS operating system, it used to be very strict about the length of the extensions and the length of the file names. Windows, current modern version of Windows doesn't care. Linux doesn't care. Okay. Character set. Can I use Turkish characters in my character set for operating systems? Some of them it is yes, some of them it is no. Okay. Do we have uniform or non-uniform file naming scheme? We'll talk about this, but it looks like I am out of time for today. I think I will continue on this starting next week on Monday. Okay, that's it for today. Are there any questions? Any questions?
So, sir, to get it clear, when we say extensions are uninterpreted or something like this, so for Linux, the operating system doesn't care about the extensions. Each program, when a programmer implements it, he has to take care of the extension of the file, right?
If you choose to, yes, but you don't have to. I mean, your program doesn't have to store your data files with a proper extension. But if you like to do that, it is your decision.
Okay, thank you.
Okay, when you in Linux, how do you know that a file is executable? When I look at them, okay, when I look at them, I don't see if a file is executable or not by looking at the just file name. That includes the extension. Of course, it says there are txt, txt, txt. Most probably these are text files, but they don't have to, right? They don't have to. To be able to understand if they are executable or not, I just check these, right? I just check these executable marks. So it looks like I don't have any executable file in this directory. How about this one? Again, when I do this, I am not seeing any clues about the executables, but I mean, my shell is nice enough to make the executable ones green, but it didn't have to. It is the function of the shell. So when I do this, I see it, right? So a dot out is executable. Okay, this prog is executable. And I can, if I move, okay, my prog to prog.txt, it is still executable, right? It is still executable. And I mean, I shouldn't do this, of course, but as I said, the system doesn't care about the extensions. If I, as I said, extension is, I mean, dot is just a simple dot, dot, and dot, dot, dot. C is a valid file name. So extension doesn't mean anything for Linux. The important thing is the data that you keep in your file, and Linux somehow knows that this is an executable program. Okay, you know this command file. Okay, it's a utility that tells you what those files are, and it doesn't look at the extension at all. Good. Okay. Any other questions? Any other questions? If I do the similar stuff with Windows, for example, let me do this, let me do this. For example, I am going to change the name for this one. Let me put this exe here. Oh, I cannot change it because I mean this one doesn't show me the extension. It's a PNG file. Can I change the extension of it by looking at the properties?
If you go to görünüm sekmesi, you can choose show
Yeah,
extensions.
görünüm, and then what?
Dosya uzantıları.
What again?
Dosya uzantıları.
Seçenekler. If I can find it.
Dosya.
Oh yeah.
Dosya.
There are three squares on the right. You can.
Ayrıntılar bölmesi. Is that?
No. On the right hand side. Yes. There is dosya adı uzantıları.
Okay. Yeah. So this is PNG, and I go there and I say, this is an executable file. It is warning me you are doing something bad because that extension is important for me. Now it's an application now. The operating system is an application. Try to run it. Okay, I cannot run it. There is something wrong with it. Okay. Good. So for Windows, extensions are important. It is interpreted and it is required. For Linux, it is not. Okay, that's it for today. See you next week.
Thank you, sir.
Bye.
Have a nice day, sir.
See you.
Have a nice day.